unknown, so features for known unknowns can produce high activations.
Yes.
And then what you want to do is to minimize that activations and maximize these activations.
Yes, because sometimes the unknown features, they have higher magnitude than known.
Yeah.
And they try to minimize the unknown features magnitude.
Yeah. So you can see it. So you can see it here. You have some features that have high response, even if they're unknowns. So what you want to do is keep their response low.
I have one question. Those are like, let's say like methods that run in parallel, or they are summing the effects of the softmax plus using the background? I mean, those graphs.
So there are three different
Exactly, there are
approaches.
three different.
Yes,
Exactly. It's not that one goes collect.
No. This
Building
is
on top
just-
of each other.
Yeah, no. This
Okay.
is just softmax thresholding. So this is showing the softmax activation in that direction and that.
So in their approach, Objectosphere, they are detaching from softmax.
They are using the softmax output, but then they multiply it by the feature magnitude.
Yeah.
So the
That is
activation magnitude.
That is this penalty thing.
Yes.
Yeah.
Because, well, they argue that since you are making it so that the feature response is going to be low, it makes sense to take that into account in your threshold. Okay?
It's kind of undone what was was done in the regulation.
Yeah, indeed. Okay. So before we get to this result, one thing that actually no, let's just go into this result because it's an interesting one. So what they're trying to show here is how the Objectosphere loss helps with differentiating the classes with respect to their magnitude. Okay. So what this is showing is how so it's normalized and how many unknowns for red or knowns for green showed an activation of that magnitude. So a feature activation. Okay, that's why it's logarithmic. Because softmax normalizes, right? So it's always up to 1. So what they show is that for normal softmax thresholding, so traditional machine learning, you get high magnitude even in the unknown classes. Okay, so you can get magnitude similar to what a known class would produce. However, when you use open set loss, you start splitting them. But since you're not minimizing the features, well, they argue that it's not because of minimizing the features, you still have some overlap here, which might be detrimental to your accuracy. And they show that with the Objectosphere loss, they are maximally separated. So the unknowns will most likely have a very small response, small activations, and then the knowns will have most likely high activations. Okay, is that clear? Yeah.
Just in terms of the subtlety of difference, though, that it looks to be the difference between those graphs looks to be that the Objectosphere loss seems to sacrifice samples from entropic open set loss. So also the curve on the entropic is smoother at the top on the Objectosphere. So there seems to be some pairing going on or something happening.
So there is no compromise here. What they're trying to show is that this overlap here doesn't exist here. So this one drops a lot more quickly.
Yeah. Because
The Objectosphere loss is trying to make those activations smaller. So of course this is the right effect that you're expecting, because you are putting a regularizing penalty on the activations, so you're forcing the network to produce low activations for the known unknowns.
And is that achieved through pruning?
No, it's regularizing. So it's this term here. So what this is doing is it's increasing the loss for for examples that have, so if you have high activation, your loss is going to be higher. So the back propagation is going to produce gradients against high activations. Okay, prior to softmax. Yeah.
Just silly question with the eta parameter, the radius of the sphere. they say that they do it like through, trying and testing parameters.
Cross validation, yeah.
Did they mention what was the final value, just to have an idea?
No, they don't. But I imagine it will be very dependent on your targets and on your known
But it's probably
unknowns.
close to the peak you observe in the known classes. It's probably sensible to assume it's around there because that's where
Yeah.
I guess.
Yeah. Yeah. It's sensible to assume. They don't show a single threshold for it. Or maybe. But yeah, they say that you get it through cross validation.
It's minor anyways.
Yeah. So I guess the main question is that yes, you have provided very nice plots to show that your loss works, but the real question is how does it work in open set loss? And this is the part I don't like about the paper, because they say, wait a second, we think that none of the metrics are right. So they provide a good 2 pages, 1.5 pages, saying why the accuracy versus confidence curve does not work, and why you can't use area under rock curve and choose an operating point or recall at k. And then they say, well, let's propose a new assessment method. Okay, the assessment method is it is sensible. So they say, bar everything they say against the traditional machine learning open set measurements. They define this correct classification rate, which there's the logical description, but it's just a fraction of samples where the correct class has maximum probability and probability greater than theta, so your threshold. Okay? So you define your threshold for softmax thresholding, then you say how many of all the samples, so of the A, of everything, well, they call the A the whole thing. So how many samples from DC, from the correct class, were classified correctly under the threshold theta. And the false positive rate is the fraction of samples from DU, so from the unknowns, that were classified as any known class with probability greater than theta. So it's actually an unknown that was, after all the regularizing and all the learning, was still classified as something known. Okay, so that's a false positive rate. And then they draw a rock-style curve, but using these two metrics.
How do they choose the theta?
Huh?
How do they choose theta?
Well, that's what this is for. You choose your operating point based on the threshold. So what we get is this. So you have your false positive rate on one axis and your correct classification rate on the other axis. Maybe.
But theta is
It's a threshold.
right.
So
Both
you
metrics
go.
depend on theta.
Huh?
Both metrics depend on theta.
Yeah. So you fix a theta. So you fix a theta and then you get that point. Then you fix the next theta and you get that point, and then you fix the next theta, you get that point. So it's a rock curve. You're just not using precision and recall. You're using other metrics.
Yeah.
They try to show here that that these three algorithms are indistinguishable using the area on the rock. That they're indistinguishable, but that they actually can have very different